Okay. So here's our attendance code. And we are in week 5. This is the week on rational expressions. What does that mean? What is a ratio? Fraction. That's a terrific example. A ratio is basically a fraction. So, it could be, 3 out of 5. If something is in a ratio of 3 to 5, then it's like 60% of it is that thing. And this is a fraction in the typical sense of the word, where it's a quotient of two numbers. But we can also have a quotient of two expressions like this. So this is like a typical ratio, and you'd call this a rational expression. It's a fraction that's built out of mathematical statements. Now, when you start talking about rational expressions, there's a new concept that's born from this that is probably the most, I would say, is the most important part of it. And it's this idea called the domain. A domain of a rational expression consists of all valid choices for x. So in that example, I just had x squared minus 1 over x plus 1. There is one number that x could not be. Because if I picked x to be this number, we'd have a problem. What's that number?
0.
It's okay to be 0. If x was 0, this would say minus 1 over 1.
1.
Negative 1. If x were negative 1, then down here in the bottom, it would say minus 1 plus 1, and you'd be dividing by 0. Can't do that. So, since we can't divide by 0, x cannot equal to minus 1. It must be different from minus 1. And what we would want to do is then write down a set of numbers called the domain, which would be all of the other numbers that aren't minus 1. And there's a couple of ways to get this done. So the modern way to do it is to say, well, I'll have all the real numbers, every number on the number line, which is what that crazy looking R is, all real numbers, but then take away, it's a minus symbol, you're used to that, taking stuff away, all the real numbers except for the set containing the number 1. This is the modern way to write such a set. It is equivalent to say something like the set of all numbers that look like this, with the stipulation that those numbers are different from minus 1. These both mean the same thing. The curly braces indicate that it is a set, it is a collection. And up here, it is a set difference. You have all the real numbers, take away this collection that has 1 point in it. And the same thing happens here. It's the set of any symbol you want, any number you want, so that that number is not this guy. Really, more properly, this should probably be all the things that are real numbers with the stipulation that it's different from minus 1. And I prefer this, but if you see this, it's just fine, and they're the same. And this just means that this symbol is an element of the real numbers. This symbol is an element of the real numbers. Both of these techniques are called set builder notation. And just to reiterate, this symbol here is the same thing as this. You can also write it in interval notation. In interval notation, that is where we would have our, it's just like having, it would be just like this picture. This is my real number line. Here's minus infinity, here's positive infinity. There's that number minus 1, and I'm just going to punch it out of the real number line. So you end up with the interval minus infinity to minus 1, union together, it's like gluing them together, union with minus 1 onto infinity. And I have parentheses here, so minus 1 is not included in this interval. And this is the same thing as all the real numbers except for minus 1. Okay, so let's go back to that example. We know that this has a domain of all the real numbers except for -1, because that's where it causes it to have a divide by zero error. But this numerator will factor, and then it would look like x minus 1 times x plus 1, and then down here is x plus 1 in the bottom. People will cross these out because they cancel. It's the same number on top and bottom. And then they will abuse the equal symbol and claim that this is equal to x minus 1. They're not actually equal to each other. They're not equal to each other because this one doesn't have a denominator. It won't have a divide by zero error. It has a domain of all real numbers. This one has a domain of all real numbers, but this one does not. That means they are different. In the homework, you will have plenty of problems that are giving you something like this, and then they say, simplify it. And the place where they're wanting you to end up is with an expression like this, where you've done the cancellation. And they will let you go ahead and say this. But there's a caveat to this, in that they aren't identical. Their graphs look just the same, with one exception. The graph of this one looks exactly like the graph of this one, except for this one is just a line that is defined for when x is -1, but right at -1, this one has a hole in the graph. So x minus 1 would have a graph that looks like this. That's x minus 1. But x squared minus 1 over x plus 1 looks exactly the same, except for right here at -1, there's nothing there, because it doesn't know what to do with -1. You can see it if I wrote it like this. You could see why that would have to be the case. So we knew that factored. You would have x plus 1 times x minus 1. And then there's an x plus 1 in the bottom. Then this just says 1 times x minus 1. And it's just like this. This is just x minus 1, except for this is not always the number 1. This is the number 1 for any value of x. This is the number 1 except when x is -1. If x is -1, it's meaningless. And that's why right here at -1, there's nothing there. But everywhere else, it just looks just like x minus 1. Right there at -1, there is something. It's -2. So that's why it's important to talk about domain when you're dealing with rational expressions. And you're going to talk about domain in the discussion board. It does not have to be anything elaborate. It doesn't even have to have anything that really cancels. You could talk about 1 over x minus 2. You know, it has a domain that's all real numbers except for 2. Don't be telling me, though, that this domain is 2, because you've got it completely backwards. The domain is not 2. The domain, in fact, is all the other numbers that are not 2. The domain is all of the numbers except for 2. That would even make more sense of why that had to be if you were to look at a graph of it. You can go to a website like this and make all kinds of graphs, and even put a graph in your post if you'd like. Right here, when x is 2, the curve wants to bend, and then it goes screaming off to either positive infinity or negative infinity as it gets closer and closer to the x value of 2. And you can see right here where it would cross the y-axis at negative 1/2. Because that's what I get when x is 0. That's what it means to cross the y-axis. X is 0, so I get negative 1/2. And as I got closer and closer to 2 on the x-axis, the x-axis is where your domain lives, right? The x-axis is a real number line, and so it would house the biggest possible domain you could have, but then it can't have this number 2, because if it did, we would look like 1 over 0. Well, evidently something that's like 1 over 0 would look like either positive infinity or negative infinity, which aren't numbers. But if I got really super close to 2, like 2.0001, then I could plug that in. I'd get 1 over 2.0001 minus 2. That's just 1 over 0.0001, which is 10,000. So it's big. 10,000 is a big number. It would be, that's why this is going up towards infinity. As I get down closer to 2, it would just keep getting larger and larger. The computation would just keep getting larger and larger. If I snuck another 0 in here, if I put another 0 right here, then I'd get 100,000. And if I put another 0 in here after that, I'd get 1,000,000. And it would just keep doing that forever. And you could make it give you as big of a number as you'd like. For however close to 2 you want to get, you could get as big of a number as you like. But you can't go right to the 2. Because if you did, then somehow infinity would be on the graph. And we'd be able to divide by 0. Can't do that. So you can make graphs of your stuff at a website like this. And your problem can be as simple as something like that. But I think they want you to do 2 problems on the discussion, to discuss 2 problems. So you could either, let's say that this was my first example, 1 over x minus 2. Well, then maybe my second example is x squared minus 4 over x minus 2. That way I can I can get that cancellation. Right? These would cancel. I would end up with this. But that equal sign has that caveat where if I had just started with x plus 2 and came to you and said, talk to me about x plus 2, you'd say the domain was all of the real numbers. But since we started back over here, there was a problem with the domain. We couldn't use the number 2. So then any simplification you do also inherits that domain restriction. Even though this says x plus 2, it's different from the regular x plus 2 in that it came from here. So it would have to have that domain restriction where it cannot include 2. Or maybe you could say that you want to do this as your example. Because here, pretty much the same thing is going on. The denominator will factor instead. And you could say that these were equal, that this was equal to 1 over x plus 2. But these are not exactly equal because the one that we started with can't use negative 2 or positive 2. Can't use either one. But this one over here knows what to do with positive 2. If I put positive 2 in here for x, I get 1/4. If I put positive 2 in over here, I get undefined. They have different domains, which is why they are equal. Their graphs would look identical. But, I mean, this one we just graphed. I drew a picture of this on the last screen. And that one would look exactly like it, except for it would have that hole when x was negative 2. Or, even still, you could discuss something like this. The domain for this thing. The denominator would factor into this. And now you can see the points that would have to be excluded from the domain are negative 1 and 2. So the whole moral of the story is that you can't divide by 0. So then when we start dealing with rational expressions, that has to be taken into account because we can't be having x plus 1 times x plus 2 equal to 0. I need it to be different from 0. And the numbers that would cause it to be equal to 0 would have to be either negative 1 or negative 2. Pick either one of those and you're going to get a 0 in the denominator. Does everybody see what we're supposed to do? Any questions? quite a bit of factoring on this week's homework, but all the factoring problems are easy. They're not any tough ones. So they're going to start us off with a couple of those factoring problems and then quickly move into stuff to do with rational expressions. The only difference between last week's factoring problems and the ones that you see this week is that last week they would have said, they wouldn't have had to equal 0, they would have just said factor. But now if you want to solve the equation, you have to factor it in the course of being able to solve it, because we are relying on a property that says if the product of two numbers is equal to 0, then it must be the case that one of them was 0. And there's just no other way for it to happen. If I've got two numbers that multiply together and the outcome is 0, then you're rest assured one of them is also 0. Or both, but at least one. Then using that idea, we want a factorization of this quadratic, and here it is, equal to 0. So then either that number is 0 or this number is 0. And those would be the solutions to the equation. So we have minus 7r minus 18. Does anybody see how to solve it right away? Either you'll see how to solve it right away, or you'll go to this without spending too long just staring at it. It's what? Negative 9 and 2. Because negative 9 plus 2 is minus 7, and negative 9 times 2 is minus 18. It has a leading coefficient of 1, so that means we know that these are the two numbers that we would use in that factorization. You'd get r minus 9 and r plus 2. But now you have a product of two things equal to 0. I have this product of two things equal to 0, so either this is 0 or this is 0. It means that r would have to be 9 or r would have to be negative 2. Those are the two numbers that when you plug them in, the equation is satisfied. And they want you to put the solutions into a solution set, which means you would plug in the correct solutions to the equation inside these brackets. And the things that go in these brackets are numbers. The numbers 9 and the number negative 2. Then that is a set of solutions to the equation. If I change the r to an x, so it just feels familiar, and say that this is an equation now that doesn't just equal 0, it equals y, just like if it was a line, y equals blah, 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 something with x, then I can sketch its graph readily because we now know that this thing factors as x minus 9 and x plus 2. So that means way over here at 9 and then over here at minus 2, that's where it would have to cross the x-axis, because right there at the point 9 we have a y value of 0. And over here, when x is minus 2, we get a y value of 0. It becomes readily evident that where it has to cross the y-axis, because if x were 0, what does it say y has to be? I want to know this ordered pair right here. When x is 0, y is negative 18. It would be 0 squared minus 7 times 0 minus 18. So that's like the easiest number to get, right? Because you're just not even considering any of the terms that have an x. It's just the constant that's left over. Describes where you're going to cross the y-axis. Now that's very much similar to what was going on in the equation for a line. If I was just talking about the line, minus 7x minus 18, the place where it crossed the y-axis was right here. Because if x were 0, then y is just minus 18. Same idea. And there is a picture of it. It makes this curve. It's called a parabola. It is a parabolic curve. These curves are symmetric. They have an axis of symmetry. That axis of symmetry is halfway between the places where it crosses the x-axis. Now the distance between this minus 2 and this 9, the distance between them is 11. Right? The distance between these two numbers is 11. So if I went half of 11 over from either point, I would be right in the middle, right on this axis of symmetry. And that number would be, well, half of 11 is 5.5. So you'd be at 3.5. Right? And then this lowest point down here, called the vertex, would have an x coordinate of 3.5. And if I wanted to know the y coordinate of that lowest point, I could just take the 3.5 and run it through this equation for x. I would take the 3.5 squared minus 7 times 3.5 minus 18, and whatever number that is that. That would be my y coordinate. And these type of curves are extremely useful. They describe all sorts of phenomena, like gravity, stuff falling, propagation of electromagnetic waves. In fact, It's getting to be old technology. Well, I don't know if it's that old, but a satellite dish is not some random old shape. It is a parabolic ellipsoid and along that axis of symmetry, parabolas have a point called a focal point. And the focal point has the property that it is positioned such that any line which is coming in parallel to the axis of symmetry would have a corresponding line that extends to the focal point, which is perpendicular to a tangent. So if you ever wondered why, it's not an accident why that little receptor on the satellite dish is where it is. It is at the focal point of that parabolic shape, so that when the signal from the satellite comes in, it will bounce off and go directly to the receiver, which is at the focal point for whatever that parabola is. So we got this. The solution set was 9 and minus 2. We're going to do the same thing here. Now, the property that we're using is that it's equal to 0. We must have it be equal to 0 so that we can have a product of two things equal to 0. If you wanted to talk about a product of two things equal to some other number, there's an unlimited possibility of ways to get that to happen. But if it's equal to 0, there's just the one way. And your answers will be unique. So it's got to be solved for 0. So you take all these other terms and move them to the other side. We would be looking at 2s squared minus 5s minus 3 equal to 0. Then I would have a times b equal to what? What did we put here for this number? Yeah, it's the leading coefficient times that constant, and then the a plus b was. So I need two numbers that multiply for minus 6 and add up to minus 5. Well, those are only 1 unit apart, so that should be reasonably easy to detect what that's going to be. One minus 6 is minus 5, and 1 times negative 6 is negative 6. So I can see how this would need to be written as 2s squared plus s minus 6s minus 3. It's still equal to 0, and now I can factor by grouping. And s factors out. I'm left with 2s plus 1. Over here, a minus 3 factors out. I'm left with 2s plus 1. And then the 2s plus 1 will factor out. And I'm left with s minus 3. And what a lot of students will do at this point is, I see way too much of this type of writing from here. They'll say, okay, I know that either of those can be 1. So 2s plus 1 equals 0, or s minus 3 equals 0. But this is like walking with a crutch when your legs are fine. You don't actually need to do this. This is a waste of writing. This is like getting out your calculator to add two numbers that are easy to add. It's plain what value of s would cause this to be 0 without me having to take the next step and add 3 to both sides. You can readily see that the number 3, if it was right here, it'd say 3 minus 3, and that's 0. You can use the same type of strategy for equations like this, because only if that thing right there, only if this thing right here said minus 1, we would have minus 1 plus 1 equal to 0. All I need to do is get this 2 to cancel. So I know that this guy has got, whatever s is, has got to have a 2 in the denominator, because that makes the 2's cancel. Well, then the numerator must just be minus 1. You would have minus 1 over 2. If that number went right there, the 2's would cancel, and it'd say minus 1 plus 1. You can certainly solve the equation if you need to, but it would be super cool if you also could just stop here and readily see the answer. It is within your capability to do so. Because the 2's have to cancel, so it's got to have a denominator of 2. Well, then the numerator must be a minus 1, because the 2's would cancel. It'd say minus 1 plus 1. This one's way easy, because it would just say 3 minus 3. I would be getting 3 and negative 1/2. And it's a solution set that they're wanting. So I put it, so they have the curly brackets already, and they're asking me for integers and simplified fractions. So that's what I gave them. Any questions? No questions? We're all good?
No,
What's up?
I didn't grasp the point very well. I always find it very difficult to solve.
Okay, let's take both questions. So where did the minus 6s come from? We studied this system over here, right? Do we know where this system is coming from?
Yes.
Okay. And it's this quotient, or it's this product that gives us negative 6. And our job would be to solve this system. We would have to produce two numbers like A and B that add together to give me a minus 5, but that multiply together to give me minus 6. So evidently, a 1 and a negative 6 are the two numbers that do it. Then the coefficient here is 1. There's my 1, and then there's my minus 6. Because 1s minus 6s, that's minus 5s. And every time, that system will tell me how to rewrite the middle terms. Make sense? All right, so where in this do we start to get stuck? Do we understand this part?
So that part, you are multiplying the 2 from the 2s by 3, by negative 3. Okay, you get negative 6.
Yes. That's our product. That's A times B every time. We're always going to multiply the leading coefficient and the constant together. And then where does the minus 5 come from? It's from right here. Okay. Somehow or another, we figure out what A and B are. There's a couple of ways to get it done. It'll either be obvious and you'll write it down right away, or you'll sneak up on it by working on this sum. Once you get that, then you rewrite the middle term. Make sense? I rewrite the middle term. And then you factor by grouping. Do you remember how to factor by grouping? Let's look at another one. Similar question. I'm going to move all the terms to the left side so that way it's equal to 0. Okay? Just follow along. Only. Okay. So I have 4a squared minus 17a minus 15 equals 0. A times B needs to be equal to what?
4 by negative 15.
When you say by, you're expressing a fraction, 4 times negative 15. So, and what is that? No. $15 and $15 is how much money?
That's 60.
Negative 60. Okay. And A plus B, so A is really busy here. Let's change this one to an X. I don't want to get, it's the same thing. And now A plus B is what?
Negative 17.
Negative 17. We would like to find the A and the B that solve this system. If they exist at all, there's just the one choice for each. All right, so give me 2 candidates for A and B, focusing on their sum being a minus 17.
15.
You're going to have to subtract an awful lot to get down to negative 17. Right? Are you thinking something like minus 2 minus 15? That's minus 17. But then minus 2 times minus 15 isn't even negative. So what must I have happen for my choices for A and B in order to get a negative product? You need exactly one of them to be negative. We have a suggestion for negative 20. Why would I use negative 20? If I put negative 20, what's the other choice for, so if negative 20 is A, what does B have to be? 3. Is this true that they add up to minus 17? Why are you writing? Look up here. Is this true that this adds up to minus 17? What is their product?
20 by 3, 60.
Negative 60. So then these are the solutions. What am I going to come back over here and do?
We are going to say x
What is the term that gets rewritten? You only have three choices. Are we going to rewrite this one? No. Are we going to rewrite this one?
Yes, we're going to rewrite 15 and 17.
No. Look at how a plus b is negative 17. That's not an accident. This is negative 17 right here. And now we have what a and b are. This one is the one that will get rewritten with that a and that b. Because minus 17 is minus 20 plus 3. So, since we have minus 20 plus 3 is minus 17, we will rewrite this middle term as a minus 20x plus 3x. It's that middle term that's getting rewritten. Remember that the point of doing this was that when we started with two things that got FOILed together, if I started off with x plus 3 times x plus 2, and I multiplied them together, I would get x squared plus 3x plus 2x plus 6. Look at how I had these two x terms that would have to get added together. Well, if I add those together and get 5x, it obscures from you how it looked before I added those terms together. And that is what's making it hard to factor. If I always showed it to you in this four-term, if I always showed it to you as these four terms, factoring would be nothing. The whole heart of the problem is determining how to rewrite the middle term so that you can see what it looked like before they were combined together to give a minus 17. Because from here, it's just factoring by grouping. Factoring by grouping, we wish all the factoring problems were that easy. Because I just looked at the first two and the second two. What do these first two have in common?
4.
And?
And x, 4x.
So a 4x factors out, and what is left over?
X minus 5.
What do the second two have in common?
3.
3 factors out, and it had better be the case that what I am left with is the same as what I had over here. If it's not, you've messed up. It is just, if this is the actual solution, then you are guaranteed that when you get to over here, they will be the same, x minus 5 in this case. Since they both have an x minus 5, then the x minus 5 factors out. You're left with 4x plus 3. It's factored. You can now see what the numbers are that satisfy the equation. 5. This one has a denominator of 4 and a numerator of minus 3. This one must have, this one must just be minus 3/4 because when I put the minus 3/4 here, the 4's cancel and it says minus 3 plus 3. And this one's just 5 minus 5. What do you think?
That one won't be minus 5. It will be a 5.
It would be 5. What is the, so if I put 5 right here, what would it say? It'd say 5 minus 5, which is what we're wanting. Because look,
Oh,
it must equal to 0. So I would need to, then it must, since this product is equal to 0, then one of them is, or even both. What's the GCF on this one?
2x.
2x. It's not 1, so I wouldn't launch off on that factoring expedition. You always want to factor out the GCF first. So I would be getting that I get 2x times x plus 6 equals to 0. How many solutions do we have? 2. Anytime you have a quadratic, anytime you factor it and get 2 unique things, you would have 2 solutions. They got to be unique, and then you'd have 2. If they're the same thing, you just have the 1 solution. But and what are those 2 solutions? 0 and negative 6. I can't tell you how often students will miss the 0. This guy right here, it's plain that if x were 0, it would say 2 times 0 times 6, which sure enough is 0. So x equal to 0 is one of the solutions. Then the other one must be negative 6. We good on this one? Let's do this one right here and then we'll take our break. So this problem is an awful lot like the example I was using when I was talking about domain. Write the rational expression in lowest terms. That means go ahead and factor the numerator and the denominator, do the cancellation, and abuse the equal symbol to say what this would simplify out to be. All right, how's that numerator factor? What's its GCF? 5. The 5 factors out, you're left with?
T minus 5.
How does that denominator factor?
T. T. Plus 5 and then T plus 5.
And this thing is called this denominator is called a what? It's a difference of 1 and 2. It's a difference of 2 squares. It's a difference of 2 squares. It factors into a conjugate pair, where these things are identical but for the minus and the plus. Okay, well, deep down, this guy is really saying t minus 5 over t minus 5 times 5 over t plus 5. And this thing here is just a 1. And since it's behaving like a 1, everywhere except for at 5. At 5, it's not 1. At 5, it's nothing. But they're not asking us about that here. This is behaving like a 1 everywhere except at 5, so we'll go ahead and cancel it, ignoring the problem at 5. And the reason I'm able to cancel it is because look, it's being this is just a 1. It's 1 times that. And according to the multiplicative identity, 1 times that is just that thing. So we get 5 over t plus 5. All right, let's take 10. It's 7:08 right now, so back at 7:18. And, well, we're nearly a third of the way through it, so. It's just more of the same from here to the end of the homework. Tell me what the question mark is. -1. Does everyone agree? Because if I distribute that -1 in, the z becomes negative, the 1 becomes positive, and that's exactly what we have going on over here. Do you see it? Try it like this. Distribute it in. Huh? You get minus z plus 1. But addition is commutative. 2 plus 1 is the same thing as 1 plus 2. So I can write this as 1 minus z. All right? This fact will come in handy several times in this assignment. And they go ahead and get us started with that right here. 1 minus c. Let me also point out that if I have a fraction, a over b, and it's got a minus symbol out here. This is the same thing as if I had minus a over b, or if I had a over minus b. They're all equivalent. They're all equivalent because having that minus symbol there is just like having a minus 1. And that minus 1 could very easily just be minus 1 over 1. Or it could be 1 over minus 1. It all comes out the same. So, if I worked out a problem and got this, where my denominator was a -1, then I might as well just say that it's whatever it is, but it's negative. So, like, for example, 5 over -1. That's just -5. Then in this problem, we'll use both those facts. And we'll also use, in the course of factoring this numerator, what's that thing called? Difference of two squares. The difference of two squares. So how does this numerator factor? And this denominator would look like a z minus 1 if only I had it multiplied by a negative 1. So I've factored the numerator, and I've essentially factored a minus 1 out of the denominator. Because I could just distribute that minus right back in. This is the exact example we looked at a second ago. But now the z minus 1's cancel. Now you could type this in, it would take it. Or you can choose to distribute it. It's up to you. They're the same. Questions here? All right. Well, let's dial up the difficulty a little bit. You want to factor everything and do some cancellation. I'll put the 5z, it's already factored. It's 5 times z. And how does that denominator there factor? Five times
3z plus 1.
Yeah, the GCF is 5. So what's left over is 3z plus 1. And wouldn't it be nice if I had a 3z plus 1 show up somewhere else? What's that numerator of the other term? Or this other fraction?
So times 3z plus 1.
And then it's divided by 3. So I am going to get cancellation on the 5's. It's 5 over 5. That's 1. I'm going to get cancellation on the 3z plus 1's. And then what's left over is a z, a 7, and a divided by 3. you're going to show me how this is a fact by telling me the form of, by telling me the way that the 1 looks like that I'm going to multiply by. I can only multiply by 1. If I multiply by anything different, you'll get a different number. So we're just going to multiply by 1. That would leave it unchanged. But you can decide how that 1's going to look. All we need to do is multiply by 1, and then the answer is immediate. What shape should this 1 take? How should it look? I will tell you that it should look like a fraction. It's got to be 1, so it's the same thing on top and bottom. 1 over a is not 1. I've got to multiply by 1, so it must be the same thing on the numerator and the denominator. A over A. If I multiply by A over A, this is 1. And according to multiplication of fractions, you just multiply straight across, so the numerator becomes 1 times A. And the denominator would be 1 over A times A. And 1 over A times A is A over A, which is 1. This is A over 1. You can expand on this idea to show how one divided by the quantity A over B, which is just some number, A over B is just some number, this is 1 divided by some number, is equal to B over A. And it's really the same trick. You can only multiply by 1, but you get to choose how that 1 looks. I will wait here for you to tell me what it is. Is that the whole thing?
A over A.
Over B over A. The numerator is B over A, and the denominator is B over A. Then, when I multiply these two fractions together, you just get 1 times B over A for the numerator. And look what happens in the denominator. These are each other's multiplicative inverse, so their product is 1. And there's our answer, B over A. This answers that classic question of if you had something that looked like 1 divided by A over B, that what you would do is to multiply by the reciprocal. We just answered the question of why you do this, because this writing right here exactly says 1 divided by A over B. And you just told me how it is that that becomes B over A. It's the reciprocal. Now we're going to use that right here. Because I have this quantity and then it's divided by this other quantity. So if you're way in the back, that is a divide symbol. I'm at the limit of what I can make it. I can't make it any bigger. So it's this amount divided by this amount. You could write it as one big compound fraction, but there's no need to. Because we can immediately rephrase that division in terms of multiplication, which at the end of the day, that's what division really is. It's a rewriting of something that's being multiplied. So, I'll factor as I go. That n squared minus 25 is a what? It is a,
N plus 5, N minus 5.
yeah, n plus 5 and n minus 5 are what?
Difference of 2 squares.
This is a difference of two squares. N plus 5 and n minus 5 are a conjugate pair. So a difference of two squares will factor always into its conjugate pair. I have this n plus 2 hanging out down here, okay. And then instead of writing this divide symbol, it will be times what? Times the reciprocal, which is exactly what we said when we said that the answer to that thing was b over a. It was the reciprocal of a over b. So this would be n over 5 minus n. Now I don't want to put 5 minus n. I'd rather write n minus 5. And if I'm going to do that, why would I want n minus 5? Because I want it to cancel with this one. But if I'm going to put n minus 5, I also need to put a negative. And since it can go top or bottom, wherever, I'll just put it up here. Now I've got everything factored, converted to multiplication. I'm ready to cancel. The n minus 5s cancel, and it looks like that's all that there is to cancel. So my answer would be minus n times n plus 5 over n plus 2. Can I do this? Why not?
The other one is a negative.
That's not why. When we were talking about domain in the beginning of class, and I had something like x squared minus 1 and x plus 1. And I was telling you that the graph of this curve looks exactly like the graph of this curve. And the reason that you could see that they would have the same looking graph is because this one you could factor as x minus 1 times x plus 1, and then down here in the bottom is the x plus 1. But instead of me just doing the cancellation here and not really truly seeing why I could cancel, let me write it like this: x minus 1 times 1. You are only able to do this cancellation when you have formed a multiplication by 1. That is why we cancel across the top and the bottom, because it's not doing anything. It's multiplying by 1. So let's get rid of those terms. And if you can't make this writing, then you can't cancel it. It has to ultimately be a product with 1. And quite often you see people that want to do something like this cancellation here. But you can't do this because it doesn't say n times 2 down here, it says n plus 2. So I can't form that product with 1. You are just stuck with all of this as your answer. Questions? Number 8. Well, this one's got a lot going on. You'll have to factor everything that you see, and you could be able to cancel any terms that are in the numerator and denominator because everything will be a product. Right? You'll factor this numerator, it'll be some product. You'll factor this numerator, it'll be some product. These things are being multiplied. It's one big product. In the denominator, it'd be a product of 4 terms. And hopefully, some of the terms from up here will match some of the terms down here. All right. And this numerator here is what? This is the difference of 2 squares. It factors into a conjugate pair of what and what? There's the easy one done. Let's look at that denominator now. You need 2 numbers that multiply for minus 24, but when you add them, you get 2. Yeah. Positive 6 minus 4. Because 6 minus 4 is 2. And 6 times negative 4 is negative 24. All right, on to the next one. That numerator, the product is 20, the sum is 9. They're both positive. Is it 1 and 8? Yes. Yeah.
In the denominator, we have x minus 2, so why is it x minus 2?
It's x minus 2 because what is oh, hold on. I meant 4, not 2. My bad. I had 2 on the brain, I think, over here. It's 6 and 4. That product wasn't even 24, you know. Okay. Very good. Thank you. 2 numbers that add up to 9, their product is 20. 5 and 4. Two numbers, their product is minus 30, and they only differ by 1. 6 and 5. Negative 6, yeah, and 5. Let me give you a hint. So their difference is very small, right? If their difference was 0, it would just be a difference of 2 squares. Like, look at this one. Two numbers that multiply together for don't look at the minus. Two numbers that multiply together for 36, but add up to nothing. Well, I guess go ahead and look at the minus. It would be minus 6 and 6, all right? So minus 6 plus 6 is 0, and minus 6 times 6 is minus 36. The point is, if you have this difference and it's very close to nothing, very close to 0, like minus 1 is pretty close to 0, then look around near the square root of this number and you'll find your solutions. Just like we looked at the square root of this thing. And those were the solutions. So here's how I did it. I said, well, this is 30. But I know the square root of 36 is 6. So I wonder if my answers are nearby to 6. And sure enough, they were. 5 times 6 was 30. And if you take the 6 to be negative, then a minus 6 plus 5 is negative 1. And minus 6 times 5 is negative 30. Now everything is factored. And it's being multiplied together, so this might as well be one big division bar. And I can start to cancel stuff. This x minus 6 cancels with this one. This x plus 6 cancels with this one. This x plus 5 cancels with this guy. I'm left with x plus 4 over x minus 4. Questions? Earlier in the semester, I told you about the definition of the sum of two fractions. And when I say definition, it means there's no technique involved here. It's like this is just what we say it is. I mean, it's just like the definition of a word. And from this definition can come a strategy on how to add two fractions. So if it looks like two fractions being added together, and I'll use all of these symbols just because they are different. That's the only, I mean, A is not B, is not C, is not D. Then by definition, this is A times D plus B times C over B times D. It's got this nice crisscrossy pattern. A times D plus B times C over b times d. It's not cross multiplication. That's something different. And this is just what it is. Now, you can see from here that if I wanted to, so you can see from here that it must be the case that if I'm going to add two fractions, that they would have to have a common denominator. Well, that's not what I mean to say. What I mean to say is I could force the condition that two fractions have a common denominator by multiplying by 1. You can see that this guy was multiplied by d over d, and this guy was multiplied by b over b. So there's my a over b times 1. And then here's 1 times c over d. So born out of this definition could come a potential strategy for how you could add two fractions without resorting always to multiplying the two denominators together. If you have the scenario where each of your fractions have denominators that don't share any factors, if the denominators don't share any factors, you would say they're coprime. If they don't share any factors, this is the shortest way to do it every time, if they don't have any factors. If they do have common factors, this strategy is shorter. You want to find something to multiply by, find some way to multiply by 1 that would leave you with the same denominator. So now, when we look at this problem, x minus 6 and x are coprime. They don't have any common factors. X minus 6 is just some number, and then this is some other number, and they're clearly different by 6. So it will be the shortest way for me to get this done is with the definition. It would be 1 times x, that's this, times this, and if you're wanting to know what to do with this minus symbol, then just call it a plus and stick the minus up here. That gets it done. And then you'd have the x minus 6 times the negative 1. And it would be divided by x minus 6 times x. It's this times this, plus this times this, over this times this. How does my numerator simplify? Six. The negative distributes, you get minus x plus 6. So it's x minus x plus 6. The numerator is 6. The denominator is just whatever it is. I cannot think of any scenario where multiplying out this denominator has an advantage. There just isn't one. Because if anything is going to happen for me that's advantageous, there would be something up here that would cancel with something down here. And if I don't have it factored, I'm not going to be able to see it. I'm not going to be able to cancel it. So there's really no advantage to multiplying out the denominator. Don't do it. Leave it factored. And so that is what I'll type in. We good? Question 10. Again, the denominators are coprime. They don't share any common factors. Then, these things must add together to be 7x times x minus 5 plus x plus 6 times 2x all over x plus 6 times x minus 5. They say write your answer in lowest terms. This means simplify the numerator, try to factor it. Because maybe you will have a factor that will cancel with one of these. And if it's there, then we take it. Okay, so to simplify this numerator, I got to distribute all this stuff. I got to distribute, combine like terms, and then factor. So we would get 7x squared minus 35x plus 2x squared plus 12x. All right. And then when I combine like terms, we get 9x squared, and then a minus 35 plus 12 is minus 23. Now 23 is what? What kind of number is 23? Prime. 23 is prime, so it has no factors of 3. So the best that I could factor out of this numerator is x. It would leave me with 9x minus 23. And 9x minus 23 ain't one of these. So factoring it from here is pointless. You can just leave it like that, and you're done. So when I'm typing in this answer, it would be smart to either click this button, so it starts you with like the framework of a fraction, or you can just hit the divide key on your keyboard and it starts an empty fraction. And then you can type in the numerator and use your arrow key to get down to the denominator. Because if you don't do that, it will only put the fraction under the last term that you wrote. And I'll just use my arrow key to go down. And there we are. Now they've got three terms. So I remember when I was in school, I was in a technical writing class, and the instructor, I forget what he was talking about, but he was saying you can't eat the hamburger all at once. You have to just take bites. You don't want to try and do this whole thing all at once. That's eating the hamburger in one bite. Do just two of them. You get something new. And then you can add those two things together. Like I'm gonna just ignore this one for now. Not ignore it, but simply tote it around like baggage. Let's just do these first. We're going to do these two first, and we'll get one expression. And then we'll add it to this one. Now, why would I want to do these first two and not, let's say, these two?
Because they have the same denominator.
They're not the same, but they're close. They are this is a difference of squares. These denominators are a conjugate pair. And when I add these two things together, by the definition, I will end up multiplying these two denominators. And so after I add these two things together with the definition, the denominator of whatever I get will be x squared minus 1. And that is going to be the easiest way to do it. So, adding together the first two terms, we would get 18x times x plus 1 minus 3 times x minus 1. And it would be over the product of these two denominators, which is x squared minus 1. And then it's minus 6 over x squared minus 1. And then look at how easy it's going to be in the next step to add these things together. I mean, I could just write it with one big division bar, put a minus 6 over here, and have x squared minus 1 on the bottom, and they're added together. So we'll need to distribute in the numerator, combine like terms, and then factor it. See what happens. 18x squared plus 18x minus 3x plus 3 minus 6 over x squared minus 1. And of course, this x squared minus 1, we know immediately what the factorization of this is. If there was going to be anything if there was going to be any denominator where I was comfortable with not having it in factored form, it'd be a difference of 2 squares, because I can immediately see what the factorization is. All right. So we'd be getting 18x squared, and then 18x minus 3x, that's 15x. And then 3 minus 6, that's minus 3. And it's over x squared minus 1. Is that the answer? What do I need to do? Okay. Should I launch off into my factoring algorithm? No, why not? GCF isn't 1. Make sure that the GCF is 1 before you start your division algorithm, and each of these is divisible by 3. What's that rule for divisibility by 3? I forget. Add the digits. If the sum of the digits is divisible by 3, then so is the number. 18 is divisible by 3 because 1 and 8 is 9. 1 and 5, it's 6. We will use that. I think it's week 7. We use it pretty extensively. Okay, so let me move to up here. A 3 will factor out, and I would be getting 6x squared plus 5x minus 1. And then it's over x minus 1, x plus 1. Now let me tell you how I can see that there's going to be a cancellation without even doing anything. Looking at this denominator, the x that would go there that makes this be 0 is a minus 1, and the x that goes there that makes it be 0 is positive 1. Those are the 2 points to exclude from the domain of this expression. Well, if I just take this positive 1, I put a 1 right there, and it says 1 minus 1, that's 0. If I put a 1 up here for x, do I also get 0? Well, it would say 6 plus 5 minus 1. That's not 0, right? So this one won't be the term that will cancel. What about this term? That's a minus 1 for x. Minus 1 plus 1, that gives you 0. If I took a minus 1 and put it up here for x, it would say 6 minus 5 minus 1. And that is 0. So minus 1 would cause us to have a 0 in the numerator and in the denominator. That means that this guy will cancel with this guy. And you'll see it when you factor it. In fact, now you would already know that one of the terms, one of the factors of the factorization must be x plus 1. Like here in the numerator, it's got to look like 3 times x plus 1 times something else. And then down here in the bottom, you'd have x minus 1, x plus 1. What's that other term, though? There's not a lot of choices for what it could be if what you already know is that they have got to multiply together to give you this. We need to end up with a -1 right here. That pigeonholes what this number has got to be. You have no other choice for what that could be, given the fact that 1 times this number has got to be -1. There's no other option. Likewise, I've got to end up right here with 6x squared. And that can't happen any other way with the knowledge that this has got to be an x. It must be the case that this is a 6x. Of course, you can always do the algorithm. A times b would be -6. A plus b would be 5. You would say 6 minus 1, that's 5. 6 times -1 is -6. And so you'd be writing 6x squared plus 6x minus x minus 1. And you factor by grouping. A 6x factors out, you're left with x plus 1. And a -1 factors out, you're left with x plus 1. Then it factors like x plus 1 times 6x minus 1, which is already what we knew. So we added them together. We added together the first two, and we chose that because we knew that we would end up with the same denominators if we just did the first two. And that made it easy to add in that third one. Okay? Distribute everything out and combine like terms, you get this. But the GCF isn't 1, so we factor out that GCF, and now we're left with a quadratic that in turn will factor, and now we can cancel the x plus 1s. So we are getting 3 times 6x minus 1 over x minus 1. Questions on this problem? I can pretty much guarantee that when you get to number 11 on the homework, you will experience the same phenomenon where these first two terms have denominators whose product is that third denominator. And so you should be adding the first two terms together all by themselves, just with our division algorithm, and then, or not our division algorithm, our addition definition, and then these next two have a common denominator, so you just add the numerators. Same thing here. It's just not a difference of two squares. These aren't a conjugate pair, but it's the same idea, right? In that their product is this other denominator. So when I add the first two terms, you would get 3 times x plus x minus 8 times 1 and then it's over x minus 8 times x, which is exactly what the other denominator is. Now these two guys have the same denominator, so we can just add numerators, but look, that's a minus 8, there's a plus 8. Minus 8 and plus 8, they're gone. They add to 0. So that numerator is looking just like 3x plus x. That's 4x. And now my x's will cancel. And we've made pretty light work here out of adding together 3 rational expressions. We got lucky a little bit, and the rest of it was a good approach. Three problems left. Let's take a quick break and then we'll come back and do these last 3 problems. And you will see that those last 3 problems are oh so easy. Like you could make a big deal out of them, but we're not gonna, you know. 5x plus x minus 2 plus 2. Okay.
So,
Add the first two together. Um, You're just following a pattern. 2 times x, and then 1 times the other denominator. Plus. No. This times this. That entire denominator times this entire numerator.
X minus 3.
Okay? And it's all over the product of these two denominators. Just put them in parentheses. Parentheses the first one, parentheses the second one. All right, there's the first two added together. Now go ahead and put the plus sign and put this other one, this last term. Look at how this denominator is the same as this denominator, right? So this is two fractions with the same denominator.
So I combine them.
Right.
2x plus x minus 2 plus 2 x minus x.
Yeah. Simplify that numerator now. Now look at what you did though. This denominator now is not factored anymore. You should always have the denominator factored. Yes. Okay. What does that numerator really say?
Same this one and this one. Same.
If I only look at that numerator, you need to combine like terms.
2x plus x
Is,
3x
okay, minus 2 plus 2 is,
1.
no,
No, minus 4.
no. Minus 2 plus 2. Minus a plus a. Minus 3 plus 3.
It's 1.
No.
Minus 2 plus 4.
Minus 2 plus 2.
It's 0.
0. 3x minus 0. Do you even need to write the minus 0 part? No, so just erase it.
So it's just 3x.
The numerator is just 3x. And the denominator, in factored form, no, factored form, the way it is right now, is factored. Do you see anything that will cancel?
Is this x?
Cancels with?
This x.
Now you're finished. All right, when we were doing linear equations in week 2, you may have had stuff that looked like, let's say, this, for example. And perhaps what they asked you to do was to take this line and write it in standard form. And standard form had some criteria. It had to end up looking like ax plus by equals c, where a, b, and c were not fractions. A, b, and c were not fractions, and that this a was positive. And it's that part about not being a fraction that I want to latch on to. Because I can make this thing not have any fractions by just multiplying through by the denominator. This is an equation. since they are equal, since the left side is equal to the right side, I can multiply on both sides by any number I want, and it will stay equal. So let's go ahead and multiply on both sides by 4. If I multiply on both sides by 4, then I would be getting 4y is equal to 4 times this stuff plus 4 times 1/4. And if I use the 4, and this thing has a 4 in the denominator, then necessarily it won't be a fraction anymore, because the 4's will cancel. It'll just be a 1. This other guy, having an 8 in its denominator, I'll also get cancellation with these 4's. So I'd be having 4y is equal to 3/2 x plus 1. I still have a fraction. I could multiply everything by 2, multiply on both sides by 2, and I would end up with 8y equals 3x plus 2. All of a sudden, I have an equivalent expression, but with no fractions. I could have just jumped straight to the 8 to begin with. That would have been perfectly fine. The thing to observe is that if I have fractions and I start multiplying everything on both sides by the denominators, then the denominators will disappear. They must, because you'll get the cancellation. And a good approach is just to look around for the biggest denominator. The one that, so you want to multiply by what's called the least common multiple of the denominators. If I list out all of my factors, then the 12 is a 3 times 2 times 2 times x, and then this x is another factor. So it's 3 times 4 times x, and this is 3 times x, and this is 3 times 4. So the collection of all of the, so here's all my factors, 3, 4, and x. The 12x is built out of all of these, the product of all of these. The 3x is built out of just the 3 and the x. And then the 12 is built out of just the 3 and the 4. If I multiply on both sides by 12x, there won't be any more fractions. This is an equation. I can do that. So, let us multiply on both sides by 12x. We would get 29 is equal to, well, let me go, so I'd have 29 over 12x, and then it's times 12x. It would be equal to 12x times 11 over 3x minus 12x times 5 over 12. Then by design, this one won't have a denominator. The 12x is canceled. Over here, you get cancellation in the x's, and you also get cancellation among the 12 and the 3, because 12 has a factor of 3. Over here, the 12's cancel, and you're left with the x. So we would have 29 is equal to 44 minus 5x. Why do I get 44?
Three. You cancel x and divide. It will be 4 by
Yeah.
4 by 11.
Yes. The x's cancel, the 3's cancel, and it would say 4 times 11. Okay. Well, then look at this easy equation we end up with. A lot more palatable than the one we started with. I'll subtract the 44 and divide by -5, and I'm done. Whatever 29 minus 44 divided by -5 is. So it's 3. For my answer, I'm not going to type x equals 3. That will be wrong. It's just this number 3. It is just this number 3. Now, what if the instructions to this problem were different? What if the instructions to this problem were different and they didn't say solve the equation, but instead they say find the domain? What is the domain of, so just look at like just this side. What's the one point I can't use? Huh? I can use 4. 11 over 12 minus 5 over 12. What's going to cause me to have a 0 in the denominator? Huh? 0. I can't put a 0 here for x because it would say 11 over 0. And if that was happening, then I would be picking this other answer choice, answer B. And look at what it says. It would say something like the domain is, and then look at this writing. It says all the numbers x where x is not, and I'd put 0 there. Now, I think that on the quiz, they end up asking you a question about domain, and there's not one on the homework. And so you're going to want to make sure you're reading the instructions carefully. I had a student that was like, I can't get it right, and she was just adding the stuff together, and it was asking, but instead it was asking for the domain. And that was the problem. I want to do the same thing here, where I can eliminate my fractions by simply multiplying by the least common multiple of the denominators. This is some number. X plus 6 is some number. 2x minus 1, a different number. So my least common multiple would need to be the product of those two. If I multiply on both sides by the product of those two numbers, there's my original equation, and now I'm multiplying on both sides by the least common multiple of the denominators. It's a common multiple, and it's the least such one. There's nothing extra there. It's got all the pieces I need and nothing more. So it's a common multiple because x plus 6 is in common with this, and so is that guy, it's in common, and it's the least such one because there's not like an extra term. Then I will have forced the cancellation of the x plus 6's over here and the 2x minus 1 term over here. And I'd be left with 2x minus 1 times x minus 2 equal to 2x plus 3 times x plus 6. This is often called cross multiply. Cross multiply is not some special thing. It's just this. You're getting rid of the fractions by multiplying on both sides by the least common multiple. In other words, there's not like some other kind of multiplication called cross multiplication. It's the same thing as regular old multiplication on both sides by the least common multiple. And we end up with this. Well, now I can multiply all this stuff together, expand it all the way out, combine like terms, additive inverse, multiplicative inverse. On the left side, I will get 2x squared minus x minus 4x and plus 2. On the right side, I will get 2x squared plus 3x plus 12x plus 18. If I subtract on both sides by the 2x squared, they're gone. If I subtract the 2x squared from over here, then I would also be subtracting 2x squared from over here. They're just gone, right? It's akin to saying if I had this term and this term, and then the 15x and the 18, and I added 2x squared to both sides, that this is what you would end up with. It's just like if I had x equals 6, and then I chose to add 3 to both sides. Then it would say x plus 3 is 9. But you have the same thing being added on both sides. You can just ditch it. So the 2x squareds, they're gone. Now we have minus 5x plus 2 equals to 15x plus 18. Move the x terms to one side, move the numbers to the other side. So I will add 5x to both sides. And then I will subtract 18 on both sides. These two add up to 0, and these two add up to 0. So 20x is equal to negative 16. Now we would end up with, so 20x is equal to a minus 16, so x must be a minus 16 over 20. But minus 16 is minus 4 times 4, and 20 is 4 times 5, so these 4's cancel, it's minus 4/5. I have one solution in my solution set, and it is minus 4/5. Questions? Okay, last problem. It would be nice if I could just choose what to multiply by from the outset and wind up with no fractions at all. However, if it happens in stages, that's fine too. If I, at first, just multiply everything by 15 and then see what I end up with, hey, that's okay. But can we maybe figure out what the least common multiple here is? I've got a y minus 5. I've got a y minus 5. I've got a 15. That 15 is 3 times 5. And I've got this 5y minus 25, which is just 5 times y minus 5. These are the three numbers. I want to identify all of the pieces I would need to multiply together to construct another number that has all of the factors needed for each one of these. Such a number will at least need a y minus 5. It will at least need a 3. It will at least need a 5. It will at least need a 5. And it will at least need a y minus 5. What's this number? I basically just said what it was. It's got to have a 5. Okay. What else has it got to have? This is a number. This whole thing cannot be separated. Right? It is this denominator. So it's like I need all of the factors that this denominator is composed of. Well, there it is. It's factored. It's just this one factor. So I can't be talking about y and minus 5. It's this whole thing. Just like the factors over here are y minus 5 and 5. In fact, just start with one of these. Let's say we started with this one. It's whatever the least common multiple is, we'll definitely need to have both of these. So it will need to have a 5. It will need to have a y minus 5. Okay, go on to the next denominator. I'm looking at the next denominator. What exists here that's missing from up there? A 3. So I need a 3 up here. Okay, go on to the next one. Is there anything that exists here that's not up there? Now then, I've got the least common multiple. It is 15 times the quantity y minus 5. If I multiply both sides by that, there won't be any fractions left. There, all I've done is multiply on both sides by the least common multiple, and I went ahead and factored this other denominator here so we could see how it's going to cancel. Okay, when this thing distributes into here, the y minus 5 terms will cancel. Like this least common multiple times that first term is just the number 15. And when this least common multiple multiplies n times the 1 over 15, the 15s will cancel. And you'll just have y minus 5. It will be equal to, well, over here the y minus 5s will cancel. And the 15 over 5 will cancel. It will just be a 3. So that whole other side over there just says 3 times negative 3. And now I just have a linear equation to solve. I didn't even have to add any fractions. Right? This thing started off with me having to add fractions, but now it's just this. And we couldn't do anything like this in the other problems because they weren't equations. Right? It was just this term, and they're added, and what is it? Well, it wasn't equal to anything. These are equal to something, so we might as well leverage that fact. Okay, so 15 plus y minus 5, that's just 10 plus y. It's equal to negative 9. Subtract 10 on both sides and you're done. That's everything. Where did the 9 come from?
So 3 by 3.
3 times 3. Anything else before we get out of here? All right, that's rational expressions. When you're doing the discussion board, it's all about domain. And the only thing to watch out for is you can't divide by 0.
And we do 2 questions, right?
2 examples. 2 examples. And they do not have to be complicated. If you make them complicated, that's on you. They should just be simple. All right, I will see you in a week.